Good afternoon. For those of you who don't know me, I'm Pamela Hughes and I manage the Friends program here at the Institute. I'm delighted to welcome all of you who are here in person and our friends who have joined on Zoom. It's a pleasure to introduce today's speaker, Adam Levine, member in the School of Natural Sciences. Adam received his BS in Theoretical and Mathematical Physics from Stanford University, where he received the Jeffrey Willick Memorial Award for Outstanding Scholarship in Astrophysics. He then went on to University of California, Berkeley to earn a PhD in physics. Before coming to IAS, Adam was a graduate fellow at the Kavli Institute for Theoretical Physics and received support from the Defense Department as a National Defense Science and Engineering Graduate Fellow. With support from the National Science Foundation, Adam is currently a long-term member here at IAS. His research aims to understand the structure of entanglement in quantum field theories and quantum gravity, using techniques from the study of conformal field theories, as well as quantum information theory and ADS-CFT. So now please join me in welcoming Adam Levine, who will speak to us today on negative energy, quantum information, and causality. We'll have time for questions following the talk.
Where did Pamela go? Oh, thanks, Pamela. That was a very nice introduction. I've never had an introduction like that before. So yeah, I'm going to be talking today about negative energy, quantum information, causality. This image slide, I don't know if any of you have seen the movie Interstellar, but this is a screen grab from the movie. This is a sort of accurate picture of what a traversable wormhole would look like if you could make a traversable wormhole. But a big part of my talk today is that it's very hard to make a traversable wormhole. I'll explain what all of that means, but first, let me just start with an overview of what I work on and why I work on it. So I'm a theoretical physicist, and I'm trying to work on sort of what is the nature of quantum gravity and what is the nature of quantum field theory. Probably those terms don't mean much to you, but specifically what I try and work on is understanding energy conditions. So conditions on how much energy or how negative energy can be in space-time, and particularly what those conditions tell us about dynamics of black holes and what is and is not possible in quantum gravity. So just briefly, quantum gravity is the study of how you combine quantum mechanics, which governs the very small, with gravitational physics, which governs black holes and cosmic length scales. But why do I work on energy conditions in particular? Quantum gravity is a big subject. There are many things you could work on. And what theoretical physicists do is we try to understand the laws of nature as they are. And in particular, one useful thing is if you have conditions that constrain what your theory could possibly do, right? We want to know why nature is the way it is. And the ultimate hope would be that nature is the way it is because it could be no other way, right? That's sort of the philosophical idea. So to see that it could be no other way, you need constraints, consistency conditions. So those constraints could, for example, come from logical self-consistency, which I'll touch on today a bit, or they could come from the fact that quantum mechanics itself has in its structure some sort of constraints. There are many constraints. I'm going to talk about one sort of aspect of constraints that you get by studying quantum gravity. And the takeaway point, what's sort of interesting in studying these constraints, these energy conditions, as I'll explain, is that they've led to, well, thinking about quantum gravity has in some ways taught us about quantum mechanics itself without gravity. It's sort of a magical thing that gravity seems to know more about quantum mechanics than we do ourselves. So you'd think to study quantum gravity, you need to know what quantum mechanics is, you need to know what gravity is, you need to just put them together. But actually, it's much more subtle than that. And somehow quantum gravity tells you more just by putting them, the act of putting them together tells you more than what you had in the beginning. So that's sort of the takeaway point. And I'm going to try and illustrate that point with one. That theme has shown up in all of this research in many ways, but I'm going to try and illustrate one way in which it shows up. And to do that, I need to describe what gravity is, or how we think about it now. In 1915, Einstein proposed the general theory of relativity, as I'm sure many of you have heard of or have heard about in the media. So what is general relativity? It's a description of gravity that says that space and time, so here, space and time are united into one object we call space-time. And you should think of space-time sort of like these surfaces. It's sort of it's a surface that can be bent, okay? It can be warped. Space and time can both be warped in some sense. And the basic idea is that particles move along geodesics in this geometry. So what is a geodesic? It's a path of least length. So if you're in a flat geometry like this lower flat plane here, a geodesic is just a straight line. It just travels in a straight, particles just travel in straight lines. So that's like in our familiar everyday example, you throw a particle and it just, if there's no other force, if you're out in outer space, let's say, it'll just travel forever on a straight path. But if you're in a curved space, it might get deflected away from this seemingly straight path. And Einstein said that this geometry, the way that this geometry is warped, space-time itself is warped, is related to how much mass is in the background space-time. Okay, or how much energy density really this is in the space-time. So this equation, these are called the Einstein field equations. These are the defining equations of general relativity, tell you how the geometry, this object on the left, doesn't matter what it is, but it's some object which tells you about the curvature of this geometry, is related to the stress energy that's sitting in the spacetime. This T mu is related to the stress energy in the spacetime. So just this, you don't need to understand this equation, just other than that it relates geometry and energy, okay? So because spacetime itself is warped, that means even light propagating on spacetime will notice the effects of gravity, right? So gravity pulls on anything with mass or anything with energy, and photons or light have energy. Photons are the particle associated to light, but you can just think about light has energy. And so it will also be pulled towards massive objects. So in particular, it will be pulled towards black holes, which are very massive objects. This animation that I'm about to show you was kindly Dr. Leah Medeiros, who's another fellow here at the Institute, was kind enough to let me use this animation that they made with their student Aniket Sharma. Leah gave a really nice talk this summer on sort of related aspects. They work on more experimental aspects of gravitational lensing, which I will now illustrate. So this is an animation of light being bent by the presence of a black hole. So these lines are the trajectory of a light ray. And as they pass by the black hole, they get bent. Their trajectories get bent. They want to fall towards the black hole. So all of these blue lines are trajectories that fall into the black hole. So let's do this again. And the red lines are ones that eventually escape, right? But what's interesting, what I want to point out and what will be crucial in this talk, what I want to illustrate, is that all of these lines bend toward the black hole, okay? They don't bend away from the black hole. They bend toward it. So what this is a statement or a manifestation of the fact that in gravity likes to focus light. Okay, this is focusing as opposed to defocusing or anti-focusing, which would be that the black hole repels the light. Okay. So this is a general fact that light rays, as you fire them around some mass, they're convex. That means they want to bend towards each other, like this image on the left. They don't do the thing on the right, okay? Why is that? Why does gravity seem to want to always focus light and not repel it? I should say that this fact ignores quantum mechanics, and I will come back to what happens in quantum mechanics later. That will be an important part of this talk. But just ignoring quantum mechanics, it seems that gravity never repels light rays, okay? This is a deep fact, actually. And why does it never repel light rays? Well, it has to do with this equation. It's called Ray-Chodori's equation. It's a fundamental equation in general relativity. And it tells you that if you have a bundle of light rays, so imagine you have, let's see here, I have 1, 2, 3, 4, 5 light rays, and I can imagine them as sort of a bundle, okay? And they have some cross-sectional area, which I'm gonna call A initial here. This is their cross-sectional area. And as you track what happens to these light rays as they move across spacetime, maybe they encounter some energy density, okay? And Raychaudhuri's equation says that the gravity always bends these rays in a concave way. They focus always, as long as the stuff that the light rays pass through has positive energy density. So somehow positive energy or positive mass, energy and mass are the same thing. So the fact that the black hole had positive mass was the reason that it focused the light, okay, somehow. So, but then you could ask the question, does gravity always, is there always positive energy density? Why does gravity want things to have positive energy density? Okay. So we'd like to know, is it possible if someone hands me a theory and they say, oh, this theory has negative energy density, I want to be able to say, nope, that's a bad theory, throw it out. Okay, that would be a great tool to advance our understanding of quantum gravity, right? Okay, so to explain why, I should say, are there any questions? Obviously, ask any questions at any time if you have any. To explain why gravity wants to focus light, I'm gonna go into a detour into wormholes. So there are many examples that illustrate why gravity likes to focus light as opposed to anti-focus it. But this is sort of the most fun one, I think. But to understand it, I need to explain to you what an Einstein-Rosen bridge is. So this is an Einstein-Rosen bridge or a wormhole. So this, what I've drawn on the left, is a picture of the spatial geometry of the space-time. So this is, say, a two-dimensional space, or maybe it's a three-dimensional space, but I've suppressed one dimension, but let's say it's a two-dimensional space. So imagine that you're a little ant living on this geometry. Okay, so you can move around in here. And this is the time equals 0 geometry of the space-time. So it might evolve in time, and it does evolve in time, as I'll explain shortly. But the idea is that there's this topology or geometry where there are curves that go through this tube and they end up on the other side. So this is called a wormhole, okay? And Einstein and Rosen realized or studied this geometry while Einstein was here at the Institute, actually. And what it turns out is that you cannot traverse this wormhole. So one thing that you would like to do is say I'm an observer, say I start out over here on the left. Is it possible for me to go through this wormhole and end up on the right? These are sort of like two different universes. They're totally disconnected. Would it be possible for me to get to another universe, for example, by going through this wormhole? And the answer is that in this situation, in this solution, this is a geometry that solves those equations that I said at the beginning, this g mu nu equals 8 pi g t mu nu. So this is a solution to Einstein's equations. It should be taken seriously. The question is, can you traverse it? And the answer is no, you can't traverse it, but why can't you traverse it? So here I said that was only the t equals 0 slice, so only at time equals 0. I'm gonna now evolve that geometry in time. And to understand that geometry a bit better, I need to draw a picture. This picture looks a little intimidating at first, but I promise it's very, very simple. The idea is the following: time goes up on the left, or everywhere. Time goes up everywhere, and space is left, right. Okay, so this geometry is just a space. This represents the t equals 0 slice of this geometry. That's the geometry at this time. And there are two exterior regions, the left exterior and the right exterior. Those are those two exterior regions here, right? And the wormhole sort of connects them. So the fact that the space connects both. But now what happens as you move up in time? There's this interior region. Now, the thing that you need to know, the important thing about this graph is that light rays move at 45 degrees, okay? Nothing can travel faster than light, so nothing can move more horizontally than 45 degrees, right? So something, if I'm a particle and I'm moving through the space-time, this is me sitting still at the center, right? This trajectory. And now if I start moving a bit, maybe I move on that trajectory. And you might think, oh, well, maybe I could just do that. But no, because that would be moving faster than light. Does that make sense? So the slope of this curve is inversely related to the speed of the object, okay? And light moves on 45 degrees in this picture. So what you see is that because you're forced to remain, you can't move faster than these curves here, you're forced to hit this squiggly line up at the future. That's called the singularity. Notice that the singularity is not a point in space, it's actually a time. It's a time when all the curvature of this geometry go to infinity. So I'll explain in a little more detail what's going on here. So I'm going to draw that picture again I drew earlier, but I'm going to neglect these asymptote, these flat wings off of the edges. And this is the Einstein-Rosen bridge at t equals 0. And again, nothing can travel faster than light. So this is that picture I just drew on the right, okay? And I'm going to draw two little cross sections of this tube here, okay? So one is this surface on the left, and one is this middle surface. And what I'm going to do is fire light rays out from these surfaces. So these light rays are going to move in this direction, and then from this guy, I'm going to fire light rays both into the left and to the right. And here, the picture is that I fire a light ray from this surface here. This guy is the middle surface, so it's at the middle of this diagram. This guy's just left, so it's here. This guy's light rays are moving to the right, so they're moving along 45 degrees this way. This guy is moving along 45 degrees this way and this way, right? And I'm going to see if this guy could ever catch up with this. Well, what happens is as time goes on, the wormhole gets longer, okay? The interior of this future region here grows. And so if you're an observer, say you're moving along these light rays, you're going to try and get to the other side, but the other side is moving away from you at the speed of light. The length of this wormhole is actually getting longer at the speed of light, and so you can never catch up to the other side, right? It's like you're in a corridor, and the corridor itself is getting longer and longer, and so you just can't reach the door on the other side, right? And how is this related to what I was saying earlier? Okay, so at t equals 0, it looks like this. At t equals 1, this surface has moved to the right a bit. It's translated because it's moving along light rays, but it doesn't catch up to the surface on the right. And then eventually it keeps going, and this tube gets skinnier and skinnier and skinnier until it hits the singularity and the tube has 0 size, okay? So the area, or the length, sorry, this should really be the length of the circle of this guy, this is our guy trying to make it out to the other side, is going to 0 as time goes on. So in other words, the light rays, remember this is my bundle of light rays, is getting, its cross-sectional area is getting smaller and smaller, okay? So in order to get this guy out, in order for it to not hit the singularity, which has 0 size, I would need to prevent these light rays from focusing. I would need to defocus these light rays in order to escape the black hole, or escape the wormhole, excuse me. So the wormhole is growing, and the reason it's growing, one way of thinking about its growth is that gravity is focusing all the light in here. It's focusing it to an infinite point, to a point of infinite density, okay, or infinite curvature. To prevent that from happening, you would need to defocus these light rays. Okay, so that means that defocusing, so I said gravity doesn't like to defocus. Well, one reason it might not like to defocus is because if you could defocus, you could traverse this wormhole. Okay, that would be the idea. You could go from one side of this wormhole out the other side and traverse it. What's wrong? Why? So maybe nature doesn't like traversable wormholes. Why doesn't nature like traversable wormholes? The reason is that traversable wormholes lead to causal paradoxes. It's not too hard, and you can ask me maybe after the talk if you're interested. Once you have a traversable wormhole, it's not very hard to convince yourself that actually you're able to use this wormhole to go back in time. You can use the wormhole you can traverse it, come out the other side, and reach yourself before you've entered the wormhole and knock yourself off the trajectory that you were going to go in to get into the wormhole in the first place. So you would lead to a causal paradox, right? This is related to this idea of the grandfather paradox. If you could travel back in time, you could go kill your grandfather, but then you weren't alive, so how could you have traveled back in time, right? So this is a logical consistency condition, that nature doesn't like traversable wormholes just because they're logically inconsistent. This is what I was talking about at the beginning, a form of one of these consistency conditions. So somehow what's going on here is that negative energy leads to defocusing of light, leads to causal paradoxes. That's sort of the takeaway of this whole. If you didn't quite follow that discussion, it doesn't matter. The basic idea is that negative energy leads to defocusing of light, or negative mass leads to defocusing of light, which leads to causal paradoxes. Okay. Here's an example of a good reason why. I think we have a question here from Carl Feinberg. Do you want
to? Regarding, I guess, the elongation of the wormhole as a consequence of focusing light. Could you, I guess, elaborate on that a little?
Yeah. The idea is that So what I was trying to say is that as this wormhole grows, I'm firing light rays off of this surface here. Think of this as a surface or as an observer that's trying to traverse the wormhole. So the observer starts outside this surface, and then it ends up in between them, right? That's in the interior. This region here is sort of the interior of the wormhole now, and it's growing. What happens as it grows is that it also shrinks in size. Okay, those two things sort of go hand in hand. So what I wanted to say is that the fact that this circle here is shrinking is related to focusing of the light rays. So you can imagine a bunch of light rays that you're shooting off of a circle. And the fact that the cross-sectional area of those light rays is going to 0 means that the circle is going to 0 size. Okay, and the fact that the circle is going to 0 size is related to the fact that they're going to hit the singularity. Does that make some sense? So the growth of the wormhole goes hand in hand with this shrinking.
Yeah, that I grasp. I guess I don't grasp the mechanism that's driving elongation.
Ah, yes, good. The mechanism is gravity. That's a great question. I don't have a wonderful answer for you, except the fact that that's what this solution to general relativity looks like. So you have these equations, much like you have Maxwell's equations to electromagnetism, and you put in some ansatz for what the stress energy in the spacetime is, and you solve for the geometry. And what Einstein and Rosen found is that in this geometry, the spacetime is expanding.
All right, it just pops out of the map. All right, understood.
Pops out of the map.
All right.
Yeah.
Okay.
But I mean, it's expanding. Sorry, I mean, another way of saying it is the reason it expands is because if it weren't expanding, you could traverse it, right? So if the wormhole weren't growing, you would be able to get across to the other side. So in some sense, it needs to be expanding. But I'm just trying to say that this expansion of the length is related to the contraction of the size of the light rays. Okay, so nature seems to avoid these, well, wants to avoid these causal paradoxes. Before I get to this, are there any other questions sort of in the next section of the talk? Right, so a troubling fact is that in quantum mechanics, energy or mass, in some sense, can be negative. You can get local negative energy densities. It's a weird quantum mechanical effect, but it happens. Let me explain an example where it happens. Sort of the canonical or the most famous example of this phenomenon is called the Casimir Effect. So imagine that you have an electric field in space, but you go into the vacuum. So that means you turn off all the electric field, you turn off everything, you're just in empty space, okay? The vacuum in quantum mechanics is not really the vacuum. So because things in quantum mechanics are fundamentally uncertain, when you say there are no particles here, you're uncertain about that. So particles and things are popping in and out of the vacuum constantly. And the picture you should really have in mind about the quantum vacuum is that it's more like a soup. It's a boiling soup of stuff popping in and out of existence constantly. Everything's fluctuating. I mean, it's very slight fluctuations because it's quantum mechanics, so we don't notice it in our day-to-day life, but it's there. And one thing you can do is you can take two conducting plates. So these two plates here are some metal plates, let's say, and you put them very close to each other in space, okay? We're in the vacuum. And now there are fluctuations in the electric field happening all the time. The electric field, just like everything in quantum mechanics, is fluctuating. And these fluctuations you can think of as sort of waves that pop in and out of existence in the electric field. And they contribute to sort of a vacuum energy of the electric field. As I said, the vacuum isn't really empty and it has an energy. And some of these fluctuations, some of these waves here, have a wavelength which is longer than the separation between these plates. Okay. What the plates do is they kill all fluctuation. They pin the size of the electric field. They make it such that the electric field doesn't actually fluctuate right at the plates. And so if you have a wavelength longer than the separation of these two plates, you don't contribute anymore to the vacuum fluctuations. So by inserting the plates, these fluctuations would have been present. Now they're not because of these plates. So the energy actually has gone down because these fluctuations contribute to the energy. So you've removed some what we call modes, but you've removed some fluctuations from the vacuum by inserting these plates. And this manifests as a very small force between these two plates. Actually, the amount of the energy gets more and more negative as you bring the plates closer and closer together. And because in nature, things like to go to lower and lower energies, right? That means the plates want to move closer and closer together. So this is called the Casimir force or the Casimir effect. And actually, this is the reason that geckos stick to walls. Geckos use effectively the Casimir effect, which is a fundamentally quantum effect to stay attached to surfaces. You might be more familiar from maybe high school chemistry, something called the van der Waals force. The van der Waals force is effectively this Casimir effect in a slightly different physical setting, but it's the same idea. Okay, so this is a negative energy density. It's negative. What I mean, you might be familiar with this fact that energies are just relative. So I can only say that something has less energy than something else. So what I mean by negative energy is that it's negative with respect to the true vacuum. So without these plates in, the energy relative to the state without these plates, the energy has gone down, okay? But wait, I said negative energy leads to defocusing, and defocusing leads to logical inconsistencies. So does that mean quantum gravity is inconsistent? We can't put gravity and quantum mechanics together? Of course not. That's not the upshot of this talk. Gravity knows about all these things, and it's smart enough to deal with them. But to understand how gravity deals with it, we need to go back in time a bit, 70s, to understand black hole thermodynamics. And the idea of black hole thermodynamics, there was this seminal work by Jacob Bekenstein, who said black holes are this region of space-time, and they should really have some entropy associated to them. And what he realized was that if you throw some hot matter into the black hole, let's say, it has some entropy, it has some information. Entropy and information are sort of related. And if you throw entropy into a black hole, that entropy has disappeared from the exterior. But we know that in the second law of thermodynamics, entropy has to increase. Disorder always has to increase. So it seems like you could make the universe less disordered by throwing everything into a black hole. But what happens is when you throw stuff in, the area or the size of the black hole grows. So what Bekenstein said is, the black hole must have an entropy and it must be related to its area. And he was right. This was like an ingenious thought experiment. And so the idea is really we should think of the area as a measure of information. How much stuff is inside the black hole? How much info is in the black hole? Bekenstein's advisor, John Wheeler, has this beautiful picture of the black hole and its area being tessellated by a bunch of zeros and ones, which are sort of encoding the state of the stuff that you threw into the black hole in some sense. And if we think of, so now if we think of area really as an entropy or really as a measure of information or quantum information, then what I should say, we should include all the entropy from the matter in the exterior so that, you know, if you have a bunch of hot stuff outside the black hole, you need to include that. And then if some of that stuff leaves this contribution and falls into the black hole, the area increases to account for the fact that the second law needs to hold. The total entropy of the space needs to increase. Okay, this is a crazy deep fact and has led to many insights in quantum gravity over the years. But there was this beautiful paper which informed a lot of my work and a lot of modern developments in this subject, which said, well, maybe what we should think of when gravity says that areas need to focus or they need to decrease, you know, the light rays need to bend towards each other. Maybe what we should really think of area as is this entropy. Okay, so what I mean is, say you have some region of space, maybe it's bounded by a circle, or in 3 dimensions, it's bounded by a sphere. There's the area of that sphere, right, which I'm going to fire my light rays from and watch as that area focuses. But also I should talk about the amount of entropy or information that's bounded by that area. And really that's what I should think of as my quantum area. And that thing should obey a focusing condition. So even though in quantum mechanics, negative energies are possible and so defocusing is possible, maybe it's possible that this quantum area never defocuses, even in quantum mechanics. So that's the idea. So focusing means that this thing, as you track its quantum area in time, it's concave down. That's what focusing means. So it's For those of you who remember your basic calc, its second derivative needs to be negative with time, okay? So this is some matter, maybe the area passes by, but maybe this matter has negative energy. Maybe it's like a Casimir effect. Well, what happens is that the area might defocus, but the total contribution focuses, okay? And thinking about this, just being inspired by black hole, I mean, these authors, when they did this, didn't prove this statement, they just conjectured it. But then they said, what does this conjecture imply? Does it imply any true facts that we know are true? And actually, it implies some very non-trivial things about just quantum mechanics in general. And it leads to new bounds on the energy that are related to the amount of information in a region. So if you have a region and some stuff falls into that region and it carries information with it, this new bound says that, well, it must carry energy. You can't gain information without giving away some energy. Energy and information are directly related. And this was a new fact. This had nothing to do with gravity. The coupling constant related to gravity is gone here. I should say this h bar is called Planck's constant, and it's very small. So this lower bound is small, but the Casimir effect is small. Okay, the Casimir effect, the energies in the Casimir effect are very small. And indeed, you can check this bound actually holds in the Casimir effect. So this is a new bound that holds in quantum mechanics, but that we got from thinking about gravity. Sort of an amazing thing. And this is obeyed by the Casimir effect, as I said. And this bound was actually proved. Shortly after this original paper, it was proved by several authors. And some of my work as a graduate student and as a postdoc has been understanding this bound. Actually, I've found within these papers here, some of my co-authors, that actually in some sense this bound on energy is actually saturated. So what we mean is it's actually more an equality. There's an approximate sign here because there are some technical subtleties to the statement, but I won't bore you with those and just say that we found that there's a direct relationship between the energy passing through some point in space and the amount of information that that energy carries with it. Okay. Okay, so I said, all right, so the Casimir effect led to defocusing. That might lead to causal paradoxes. But what happened was actually, if you think more carefully about negative energies in quantum gravity, you find these new bounds. Carl, there's a, yeah, you want to ask a question? I think so. Oh no, I'm not. Well, I'll just keep going until. So the idea is that these new bounds that we got from thinking about gravity actually imply something a little bit weaker. They imply just the right thing to make this wormhole remain non-traversable, even when the Casimir effect is taken into account. If you use those bounds that I wrote down, what they end up saying is that maybe someone can throw in some negative energy here, okay? And this can cause the wormhole to stop growing. But what those bounds tell you is that no matter if you throw in negative energy at some time, you have to compensate it always so that the total energy that an observer trying to traverse the wormhole sees is always positive. This means the net focusing of that observer is always positive, and so they will always end up hitting the singularity. So these bounds prevent this wormhole from being traversed, even in quantum mechanics, okay? So they account for the fact that local energy can be negative, and while preserving the fact that gravity is self-consistent, quantum gravity is self-consistent. So this was, what I wanted to illustrate was that we started with some classical gravity, non-quantum gravity setup, and then we got ourselves confused when we tried to include quantum mechanics. But somehow by thinking about quantum gravity, namely black hole thermodynamics, we were led to new bounds that actually told us new things about quantum mechanics that we didn't know before. And this has been a theme that's occurring all over the place in recent years in this work. And so I'm certain that there are many more insights that quantum gravity can tell us about quantum mechanics. And of course, vice versa, that's the ultimate goal. But I hope to learn many of them in the coming years, but that's the basic idea. Yeah, thank you.
Can I ask a question?
Yeah.
Yeah. Do you have the opportunity to use algebraic geometry in your work?
I personally do not, but many people in the study of string theory do. I think, yeah, I would love to. No, I do not. Let me just put it that way before I speculate on maybe ways.
I mean, are there reasons why some people use algebraic geometry with quantum mechanics, or there are reasons not to use it? What is the philosophy behind it?
Well, unfortunately, I don't know a ton of algebraic geometry, but my understanding is that algebraic geometry has been used in a lot of interesting ways in understanding exactly what. So in string theory, there are these. There's this problem that string theory predicts that there are 10 space-time dimensions.
Mhm.
String theory is sort of our best candidate of a consistent theory of quantum gravity.
Mhm.
And so you need to explain away these extra 6. We live in 3 + 1 time, 3 space dimensions plus 1 time, so 4 dimensions. String theory predicts 10, so we have
Well,
6.
could you start from which fields have polynomial equations?
Yes.
And relate to it that way. Does string theory have a lot of polynomial
Yes.
equations?
Yeah, well, you want it. So you want to describe these manifolds that you're compactifying your space. So you need to, in some sense, get rid of these 6 extra dimensions to describe our 4 in string theory.
Mm-hmm.
And the way you do that is you postulate that these 6 extra dimensions are very small. They're curled up. They're called compactified.
Mm-hmm.
And the way you describe these types of extra dimensions is via, I think in certain cases, via these polynomial.
Thank you.
Yeah. But I'm definitely not an expert in that, but I think it's a huge, rich, and amazing story there. Oh, sorry. Yes, I think there's a question here.
Right. Regarding saturation and a rough equality, could you elaborate on that? Almost define saturation, nuances in that context.
Yeah. Yeah. I could give a whole lecture. I've given many whole lectures on that. But the basic idea is, in what sense do I mean? So here, the bound that you get is a relation on the local energy density and in some sense a second derivative. It's really an acceleration in how much information gain you're getting from the matter. And what do you mean by this? What do we mean by the second derivative? Well, when we have these light rays, you could imagine following the light rays in various different ways. So you could deform the surface. So your surface is propagating out at the speed of light, but maybe you think about deforming only part of the surface along the light rays. Okay, so only a little part of the surface. So now you get some weird, deformed surface. Maybe I can draw a picture. So normally, like if we have a sphere, maybe this is a sphere, and we shoot light rays out from it, it grows in a spherical way everywhere, right? This would be like if I had a flashlight. Sorry, I don't know if they can. Yeah. Is this good? So I could do deformations of this surface along these light rays. And so, for example, I could move the whole surface out along all these light rays, or I could choose to maybe move only a portion of the surface out along a light ray like this, right? And then I get some funny, then instead of tracking the whole surface along these light rays, I'm just tracking sort of a portion of the surface. So the surface is moving in some funny way. It's getting deformed. And these derivatives that I'm talking about here are really with respect to how does the entropy change as I change the region. This d by dt means I'm changing the region in one of these very funny, sort of very sharply peaked deformations. It's a very technical statement, unfortunately, and I don't have great intuition even to this day. It's something that we sort of discovered, and still, to be honest, don't have a full understanding of it. I think there's more work to be done in really understanding.
Why not just ask you to define saturation in this context? I'm not.
Yeah. So in that context, Yeah,
Yeah.
so the bound says that the energy is lower bounded by a second derivative of the information. So the information contained in this funny space here. It's so the local energy at sort of this point that's passing through the surface here is bounded by the change, the second derivative in the entropy at that point, or using those funny deformations. And what we found is that this bound is actually an equality in a broad class of cases. So that
What is it that's saturated? That's what I'm missing. Is it the information, the entropy, what?
The term saturation just means, yeah, that's right. So the information for the amount of energy that's passing through the surface, the information gain is as large as it could possibly be by this bound.
Okay, fine. Thank you.
Yeah, saturation just means that an inequality has been turned into an equality. Sorry, it's sort of technical jargon, but.
Other questions, either in the room or on Zoom?
Yeah.
For you, and that is, could you talk a little bit about your institute appointment? And you came here as a postdoc, right?
Yeah.
And you've got a 3-year appointment, and just
Yes.
sort of what that's like and what's next.
Yeah, what's next? It's I mean, it's been like a total dream for me to be here. Ever since I was a little kid, I've wanted to work at the institute. I mean, and it's lived up to my hopes. I've been able to talk to people that I've, read many papers of, and get to talk to them every day at lunch, walk into their office, talk to them. Everybody's been, I don't know, so yeah. Everyone's been super inviting, which was actually sort of a surprise. Sometimes you get intimidated by these people, but they're actually very much not intimidating. Yeah, it's been a total dream. My next, I'm probably going to do another postdoc and then apply for faculty positions. So it's my, and as far as physics goes, I'm going to continue thinking about this quantum null energy condition, or this energy condition that I talked about, has led to a lot of interesting calculations that I'm still sort of working on now, trying to understand the manifestation of this energy condition in various systems. So there's a lot of work to be done there still. Yeah. Oh yeah. I saw that.
Ush.
Yeah, can you hear me?
Yeah.
Yeah, I had sent a question. I don't know how sensible this question is. Looks like it could be totally out of the league. Please pardon me. I'm not a physicist. I'm a physician.
Yes.
So just from a layman point of view, what differs the locations of the wormholes? For example, can one wormhole lead to universe A and another lead to universe B? Please decide to not answer this question if it is too stupid a question. Okay.
Oh, no. No, yeah. So I think it is what you're asking, that I could have wormholes connecting. Yeah, I mean, one funny thing about wormholes is that you could have wormholes connecting totally disconnected universes. That's like a well-defined mathematical thing that you can study. And yeah, you could have one universe over here, another universe over here. They're connected via a bridge, but not connected anywhere else. So yeah, you could have one wormhole go to one universe, another wormhole go to another universe. I mean, you could have connections all over the place. Actually, in a very hot topic of study right now is trying to understand this fact that it seems like gravity sometimes leads to these connections between universes that are totally disconnected, which is a bit confusing.
So
What
what determines the destination of the wormhole? Is there anything which defines that?
Yeah, so at the level of math, you can just study solutions that have a wormhole connecting one universe to another. If you actually want, if you say, oh, you said, if you say nature actually does have these wormholes, like our universe, there are actually two universes, maybe we live in a multiverse, and there's a wormhole connecting our universe to another universe. I wouldn't know how such a thing, it would depend on the details of the problem, how you might come up with such a situation dynamically. So meaning like from the Big Bang, could wormholes form between one universe and another? I don't know the answer to that question, but it's interesting.
Of course. No, but thank you so much, at least for taking the question. I was even hesitant to even ask.
Adam, it was a really great presentation. Do you have any recommendations as to writers? I know Gribben has written a lot about this, Gribben, and other writers or scientists, anything that you would recommend or that you yourself have written that would be really for the layperson, but would open this up? And thank you so much. A very wonderful presentation.
Thanks. I mean, the classic, which maybe you've already read, is Brief History of Time by Stephen Hawking. That's a wonderful, and there's a new edition, which has really nice illustrations. The original didn't have now computer illustrations are a lot better. So now it has really, really beautiful illustrations of wormholes. And I think they talk about a lot of, I discussed, not the modern developments, that's modern, that's, after Hawking's time, but up to sort of the, the lengthening of the wormhole, I'm sure they discussed that. And actually something I was reading in preparation for this talk was this book by Kip Thorne, he's worked a lot on this. He's a professor at Caltech, Kipthorne. He has a book on the physics of Interstellar, the movie, where he talks about a lot of because he did a lot of work on that movie, sort of making sure they were being sort of honest about the science. So he goes through sort of all the different scenes in the movie and talks about various, and I think that's also probably a pretty good book. It is a good book, I've read it. But yeah, those two are sort of the classics, or sorry, Brief History of Time is a classic. That's